Okay, very good. Well, good afternoon, everybody. My name is Pedro Diniz, and I'm currently with the ENESC-ID in Lisbon. And it is my pleasure to moderate another presentation on the quantum computing talks organized by the Faculty of Engineering at the University of Porto, among other departments at the University of Porto. And today we have the pleasure of having the two speakers from the Cineca High Performance Computing Center in Italy, who are going to tell us about their ongoing efforts or related research going on at that center. And they are Riccardo Mengoni and Daniele Ottaviani. So let me first briefly introduce them and then give them the floor. Riccardo Mengoni graduated from the University of Verona, focused on quantum machine learning. And since 2018, he has joined the Quantum Computing Lab at Cineca, currently led, in fact, by Daniele Ottaviani, who is a mathematician, let's say, by education, but moved on with his graduate studies in high performance computing. And as I mentioned, since 2020, he's the coordinator of the Cineca Quantum Computing Lab. So they're going to tell us what's going on at Cineca, and in particularly, I think it's very interesting, this synergistic relationship between quantum computing and high performance computing. So please welcome and take it away.
Hi, Pedro. Thanks for the invitation and good evening to everyone. I will leave the floor to my colleague Riccardo Mengoni in order to start this presentation. And thanks again for this opportunity.
Thank you. Thank you so much for the invitation. It's a pleasure for us to be here talking about what we do in quantum computing at Cineca. So yeah, again, I'm Riccardo Mengoni. Hello, everyone. First of all, let me just briefly introduce you what Cineca is about, what we do. So. Okay, Cineca basically is a consortium composed of 98 Italian universities and public institutions. And since the 70s, basically, Cineca has given support to scientific research, both to the public, which means universities, and to industries, medium large companies in Italy. It has done this via so providing supercomputing access and expertise for what concerns high performance computation. And so today, at Cineca, we are the high performance computing center in Italy, and we have one of the most powerful supercomputer in Europe, which is Marconi 100 right now with 32 petaflop peak performance, so petaflop 10 to the 15 floating point operation per second. Okay, for those of you that don't know this, there is actually a list of the 500 most powerful supercomputers in the world. Actually, Marconi 100 is in position 14, and coming soon. So we have, we're gonna have Leonardo, who is gonna be our pre-exascale supercomputer. It's gonna be activated in 2022 probably, and it's gonna project us in the top 5 of the same list. Okay, so actually, so Cineca is a center of excellence in Europe and worldwide for what concern HPC since the 70s, and it's been a couple of years since we started our quantum computing lab. So here we have here with my colleague Daniele, which is the coordinator of the project that we do at the Quantum Computing Lab at Cineca. So basically, we collaborate with different universities, industries in Italy, and also quantum computing startups in Europe, and through a variety of projects. And we also give the opportunity to Italian students to have internship courses. And every year we organize a conference about the interplay between HPC and QC, which we call HPC QC. So here you can see our website, so feel free or our email. So feel free to drop us a line, contact us, or visit our website for more information about what we do or any collaboration with us. Okay, so let me start with the core of this presentation. I'm gonna just briefly overview something about some concept of quantum computing that I find relevant, that are relevant for us. So, okay, let's start with what we call the old school quantum algorithm. So this kind of algorithm that everybody knows, like the Shor algorithm, Grover search, and others, quantum chemistry simulation. So this algorithm came up in the 90s, and we know we have the mathematical proof of their speed up with respect to the best classical algorithm. Okay, so one example here that I always like to show is the Shor algorithm, okay, for factorization of numbers. So basically, if you imagine that you could use the most powerful classical supercomputer that we have today, and the most powerful, let's say, also algorithm that is a number field sieve, so the most, let's say, the best classical algorithm that we know. And if you want to solve, to factor a 2048 digit number using the most powerful supercomputer and the most powerful algorithm, classical algorithm, is going to take us billions of years. So something of the order of the age of the universe, probably. Instead, with Shor algorithm, if assuming that we have a fault-tolerant quantum computer capable of executing Shor algorithm with at a gate rate which is reasonable, then it will take just a matter of seconds to factor the same number. Okay, so say ideally, we know since the 90s that quantum. So what are the potential of quantum computers and why? So we will never be able to build a high-performance computing center or a supercomputer that will be able to perform as well as a quantum computer, a fault-tolerant quantum computer. So okay, however, okay, there is so from the mathematical point of view, we know that. From the more practical point of view, this kind of algorithms are gonna require error correction, okay, which means an overhead in the number of qubits. So we probably will be able to run this kind of algorithm with a provable speed up on computers, quantum computers with something like 1 million or hundreds of thousands of qubits. So we're still far from this regime, and probably by looking at the roadmaps that companies have, we will be in this regime in 10, 20 years, but nobody is sure about how or when exactly. So, and now what we are living today is this NISQ era, which stands for noise intermediate scale quantum. So intermediate scale small quantum computers, which are noisy, so which do not use error correction, probably like I mean, probably other form of correction like error mitigation, but still no error correction. And we know that so right now we have these two kind of devices available to us. On one side, quantum annealers, so special purpose quantum devices that run this algorithm that is quantum annealing, and the other one are quantum computers, which are programmable digital quantum computers based on circuits. Okay. So basically, the scientific community and also us from the Cineca Quantum Computing Lab are pretty confident about. So we strongly believe that this NISQ technology could outperform. So in the NISQ era, these outperform traditional classical computers. So in even high performance computer centers for specific applications. Okay, what do we mean by outperform? So outperform can be seen at different levels. So one is speed up, so like for short algorithm or Grover search, so which means finding probably the same solutions that a classical computer would find, but much faster. The other thing is we could find also better quality solutions. So if we compare with the state-of-the-art, let's say heuristic classical solvers, so probably we could be able to find a better solution in the same amount of time, or maybe spending a little bit more time. This is due to the fact that, of course, with quantum effects, you could be able to see patterns, for example, or use features that are proper of the quantum system that you do not have usually in classical computing. The third part, which is usually probably not very underestimated, it's lower energy consumption. So could be that quantum computers will be able to find solutions consuming less energy. Early studies, in fact, has shown us that, of course, we know that supercomputers require a lot of energy in order to run. Quantum computers probably are going to need energy. So the large part of the energy is going to go in the refrigerator, but it seems that probably there is not much energy required for the refrigeration when you scale the system up. So when you scale the number of qubits. Okay, so this is our idea. Okay. For what concerns the specific applications, these are the hottest topic right now: quantum chemistry, quantum optimization, and of course quantum AI and machine learning. Okay. So this leads me to our, let's say, first concept about the Cineca vision of quantum computation. So something that I would like to state is that quantum computing, to us, so our idea of quantum computing is that it will always be hybrid. So it means at least we will always have something like a pre-processing part or post-processing part that is going to be run on an HPC, so a classical HPC set. Okay, and it's going to be probably this back and forth between the QPU and the HPC. So first concept is we don't see the quantum computing as something that goes alone. Okay, it is separated from HPC. Okay, we really see them in a hybrid environment. So in this, with this idea in mind, we are working, let's say, in 4 different directions. One is emulators. So emulators are, by emulator I mean classical software that emulates quantum system or quantum computer. So that emulates, or in other contexts, people say simulate. So they can simulate the full Hilbert space, let's say, or in a smart way, you can reduce the complexity of the space. So basically, we are developing HPC ready software for emulating quantum computers, quantum system, and also testing state-of-the-art simulators, emulators, that are available to the public. That's for what concerns emulators. Hybrid workflows. So we are developing workflows that take into account both the hybrid nature of the algorithm, so algorithm that that work both on the QPU and on the CPU and the HPC side, but also workflows that are problem oriented. So depending on which kind of problem you are addressing, there is a different workflow for your approach. Third is scheduling. So scheduling, of course, means ensuring that a task is run with the resource it needs, and also decide how to allocate in a smart way the hybrid QPU and HPC resources. And finally, the fourth level of our work is on applications, on real-world application, let's say. And as I said before, these go in the direction of chemistry optimization, machine learning, and also simulation of quantum system. Okay. So let's now a little bit focus on emulator part. So one may ask, why is it relevant to have an emulator if the Hilbert space grows exponentially with the number of qubits? So at some point you're not gonna be able to emulate anything. So actually, emulators are very useful instead for different reasons. One could be the development and verification of quantum algorithm, benchmarking. You can study noise, so basically how noise affects your quantum algorithm. So you can run emulation of your quantum algorithm in a noiseless way, of course, or how noise affects the algorithm, or study the noise of your quantum device, and in this way then assess other hardware constraint and study how topology of the hardware affect the algorithm. And again, one can think also to emulator driven co-design of quantum algorithm depending on the result of this emulation. And okay, many others things like compilation. Okay, everything that needs that is a reliable simulation of the quantum system of quantum computer to run. So it's better to. So there are a lot of usages for emulators, and it's better to have a fast emulator because increasing the dimension of the quantum system, it takes a lot of time. And okay, that's why we tested basically a multi-thread, single node multi-thread version of Qiskit and Cirq, which probably not many people are aware, but Qiskit and Cirq have inside this multi-thread single node version which works with OpenMP and provides state-of-the-art emulation for quantum circuits. And we're also working on with the QTIP developers about the multi-thread multi-node implementation of QTIP, which is another quantum another classical software for emulation of quantum system and quantum circuits. Okay, these are some results that we got from our emulation, state vector emulation. So state vector means that computes the whole Hilbert space with Qiskit and Cirq. So we were able to run with a single node up to 128 threads using Marconi 100, and also another system that we have that is called Galileo 100. And we were able to run quite complex algorithms, like quantum Fourier transform, quantum volume, and so on, in a reasonable amount of time using a single node and this amount of threads. And we were able to reach the 34 qubit limit. Okay. Then, so in 100, let's say 2000 seconds. Then, for what concern tensor network emulators, so before we talk about state vector emulator, for what tensor network we are we developed one MPS emulator together with University of Padua, which is developed in Fortran, and also has the QComms, which is an interface for Qiskit and Xanadu Subaru Fields. Subaru Fields basically is software for photonic quantum computation. And we're also working on a parallelized implementation of this MPS emulator. So we have some early results also here, and which show that our MPS emulator is very stable, and also increasing the problem size, it is able to, for what concerns the computational time, it easily beat the MPS that is built in Qiskit by an order of magnitude. Okay, and we were able to reach also more than, say, hundreds of qubits in the emulation, fixing, of course, the bond dimension key, which basically tells you how good is your approximation that you're doing with the MPS. Okay, for what concerns quantum annealing, instead we are relying on the D-Wave library for simulated annealing, but also we are working on Squad, which was developed by Riccardo Mengoni from NVIDIA, which uses also multiple GPUs for the simulated quantum annealing. Okay, and that was it for what concerned emulators. Now, how we see these hybrid workflows so hybrid algorithm that take into account the QPU and the HPC part. So we basically thought about three different possible scenarios. One is what we call the QPU enhanced computation, where basically we have a problem, and it's mainly addressed by a classical algorithm run on CPU or in high-performance computing center, so by supercomputer. And then we have some computational intensive subroutine that are sent to the QPU, and this could be in a far-fetched, let's say, scenario. Could be, let's say, something like Grover search that goes to the quantum algorithm. In a more realistic, let's say, short-term vision, could be something like kernel estimator for support vector machines, so quantum kernel estimators, so in a quantum machine learning context. So this means that at the end you get a result from the QPU, which of course is fed inside the classical algorithm. Okay. The second type of workflow could be, let's say, competing QPU CPU, where basically the QPU and the CPU compete to find the solution to the same problem. And basically at the end you can either select the best solution depending on which are your parameters, or combine the two classical and quantum solution. Okay. The third part, which is basically the one that today people are, so the approach that today is more widespread and so which research centers and companies are studying, is this what we call iterative hybrid algorithm, where basically again we have a problem at the beginning and we try to address it via a quantum algorithm, which is a parametric quantum circuit, basically, which is run by some QPU, and depending on the measurement you can compute a loss function, let's say, which is optimized via the HPC system. Okay, and then and which again optimize, let's say, the circuit and updates the parameter, which again is sent to the QPU. So, and this is an iterative approach, and we have this back and forth between the QPU and the HPC system until we reach some kind of convergence and we are satisfied with the solution. Of course, and this okay, what we expect is that in the next probably 5 years also to have one QPU, okay, in our facility. So this hybrid algorithm, okay, considered, let's say, just one QPU, okay, but in principle could be extended to multiple QPUs. So if you have multiple, if you can access multiple QPUs, so you can also parallel the computation over different QPUs. However, for what concern, so the scheduling, so ensuring how to split resources in the correct way, and let's say how to allocate and ask for resources in the best way. So what we have today is this situation here, especially for these hybrid approaches, where you define your quantum circuit, then you ask for the QPU access, and every iteration, so especially so if you have this hybrid workflow, every iteration you have to stay in the queue and wait for your turn. So and this means that hybrid workflows, iterative workflows may require, let's say, amount of total computation, both HPC and QPU computation, because of this queue. So what we are working on, and I think this is the direction that also IBM and other like AWS is taking, is to develop, let's say, hybrid programs, which also has inside the scheduler for both the HPC and the QPU resources. So this way you only request for resources once, so one time in the queue, and then you are so you booked both the HPC and the QPU resources, and you can perform your computation, reducing so this latency. The other thing is that since we hope to have in the future a QPU in our facility, having a QPU directly connected to our HPC systems means to eliminate, so or reduce as much as possible the latency between the communication between the two, the HPC, the classical part, and the QPU part. Okay, that may also speed up even more the whole process. Okay, real world applications. Of course, we are working on algorithms basically in two different directions. One with concerning the gate model, so quantum circuits. So this means quantum chemistry. In quantum chemistry regime, we have VQE. Quantum optimization, we have quantum approximate optimization algorithm. And for concern quantum machine learning, we have QNNs or quantum support vector machines. So we're working in these three directions for gate model. For quantum annealing, also we did some studies together, for example, molecular unfolding, where we had to find the optimal unfolded configuration of proteins. And this is, let's say, an important step in the docking process. But again, it's possible to find a quantum annealing version of the Shor algorithm for factorization, or again, it's possible to solve even a system of equation with the quantum annealer. So we work in these three applications which are relevant in different scenarios, in different applications. Okay, then I'm gonna basically leave you with this question. So, are we gonna be able to have a quantum advantage in the NISQ era? So this is the question that we are trying to answer, and we are confident that, especially with this hybrid HPC and quantum environment, we will be able to answer this question in a positive way. And we are helping researchers in Italy and in Europe and companies to answer these questions. And we're doing this via a series of projects at various levels. and I'm gonna leave the word to Daniele, that is gonna explain you which are all these projects. And Daniele is the coordinator, in fact, of the Quantum Computing Lab, and is going to give an overview of everything we do project-wise.
Thank you, Riccardo.
Yeah, please.
Thank you for your presentation. And yes, you've seen from Riccardo's presentation that the relationship between quantum computing and HPC is very important, in particular in this, let's say, this historical period when our quantum computers are not so powerful in order to be used as a standalone to implement the most important, the most powerful quantum algorithms like Shor algorithm or Grover algorithms or the algorithms that Riccardo showed to you in this presentation. But we are in a period when NISQ computers are going to be a reality, okay? And we know from literature that with NISQ computers, we can have a quantum advantage in using them as accelerator for HPC. So right now, HPC is very important. And what we are going to do in this field is to integrate as in a better way possible quantum simulation, quantum computing, and quantum annealing with HPC. One of the most, we are involved in a lot of projects in this view, but one of the most important projects that I like to mention in this talk is the HPC-QS project. We are part of the USRA HPC joint undertaking, also from the HPC part, of course, but in particular as Quantum Computing Lab, we are also part of the HPC-QS project. That is a pilot that started on this December. It's almost 2 months started, but our goal is in 4 or 5 years to realize a network of quantum simulators that are real quantum computers, not simulators in the sense of emulator, of course, but we want to connect this particular kind of quantum computer on our HPC supercomputers in order to realize a network of simulators connected one each other in order to reduce as best as possible the latency between the communication from a quantum computer to an HPC computer and vice versa. Okay, this is a real problem, and we are working with all the European, almost every European supercomputing center and important facilities in order to achieve this particular project. And also, Riccardo, please slide. Thank you. And okay, this is our, this was an example of our commitment in the European view of this in quantum computing, but also in Italy, we are realizing a network for helping our universities and research bodies to approach this new technology. Okay? Because we know right now that we have a lot of different kinds of quantum computers that we can use. We can distinguish them also from general purpose quantum computers and quantum annealers and quantum simulators, but also general purpose quantum computers are different one of each other, because we know that we can realize a general purpose quantum computer with superconducting qubits, with ion trapped qubits, with a lot of different technologies and we don't know right now what is the best technology to use in order to realize a perfect qubit. We don't have perfect qubits right now. And for this reason, we decided not to buy a quantum computer right now as Cineca, okay? And we are waiting to see if it will be possible to acquire a computer in the future. But right now, we want also to offer the possibility to use quantum computers to our universities. In this view, we started a series of projects of collaborations with different entities in the field of quantum computing. For example, D-Wave with their quantum annealers and Pascal with their quantum simulators with neutral atoms. We started this collaboration last year. Next year, we will have more collaboration with, of course, European partners, and we will offer their computational time to our user in order to teach them in some way, not only in this with this service, of course, but this will be a way to give them the possibility to use the more numerous possible quantum computing technology solutions in this particular historical time. And of course, we are also developing, like Riccardo was saying before in his presentation, we are also developing different kind of emulators. Our Tier 0 and Tier 1 supercomputers, Marconi 100 and Galileo 100, are equipped with open source quantum HPC emulators, and we are also developing better emulators than respect to the ones that are actually present in the literature in the market. And okay, thank you. Also, we are organizing a series of events in order to introduce quantum computing to our universities and to give them the possibility to assist to the scientific works that we are collecting in our work. So we are we organized a school that is Introduction to Quantum Computing School, and this introduction is freely you can freely see the videos of our intervention in our website. That maybe Riccardo, if you can write our website in the chat during this, because we have a website that we can use to store all our initiatives and projects and news and everything. And this year we organized also the 4th edition of the workshop HPC and Quantum Computing. That is a workshop started in 2018, and its purpose is to show to the scientific community, Italian and not only, because since last year we are also organizing the online event, online edition of this workshop. And in this workshop you can see what are the most recent works in the field of quantum computing, and in particular with the relationship with the high performance computing. Also in this slide you can see our last workshop that was the 15th and 16th of December this year, and next year we will organize another edition, of course, hopefully in presence and also online, because it's a very powerful tool that we have right now. And on the right, you can see a lot of logos of our partners that we are working with in order to realize the most comprehensive offer in the field of quantum computing that we can do. And with this, I thank you for your attention. We hope that you enjoyed our talk. And thanks again for your invitation. It was really an honor to be here. Thanks.
Okay. Thank you very much, Riccardo and Daniele, for this broad view, an excellent presentation on this broad view of Cineca's role, let's say, in bringing quantum computing to HPC in particular. I have a couple of questions, but I'm going to basically be giving the floor to other people here. And since they might not be muted, I'm essentially going to rephrase their questions. So that was a kind of more general question. That was about how can we become a partner to access these computers? So I mean, what is the cost model for a user to begin with? How much does it cost? I mean, how do you do it, right?
So right now, Cineca is a consortium, composed by a certain number of universities and research bodies in Italy. So right now, our offer is only for Italian research bodies and universities, because we are we are serving our consortium. And in the future, we are working also on starting some kind of project that will be at a European level. Okay, so we will not be the only one that who offer quantum computing time, but we will distribute this time also in, with our European partner. But right now, we can only serve Italian and universities and research bodies.
Right, right. Okay, because typically in these models, you usually apply, there's some grant money that you can apply either through European funds to basically access to your times, and essentially you use the funding from your project to pay your time. So, okay, all right, so good. And I noticed that Riccardo in the meantime posted here a website, and I'm sure hopefully people will get to that. So good. I had a couple of questions, but let me also rephrase another question that Anuj mentioned here, and it's fairly technical, which is how developments in quantum RAM, QRAM, will improve the parallel processing across multiple QPUs and its integration with HPC. That's his question. I hope that this makes sense to either of you.
Yeah, probably I can answer this. I mean, quantum. Okay, let me say a few words. So I started. I did my PhD started in 2016 in quantum machine learning. So in 2016 there were some early papers on quantum machine learning, probably some from by Seth Lloyd or so. So there are many algorithms that, especially in quantum machine learning, that assume to have at the beginning a quantum RAM. Okay, so it would be great to have. As far as I know, there are several proposals for building a quantum RAM, and yeah, it will be very helpful because, of course, yeah, one of the problem also related also to quantum neural networks, that is a very like hot topic right now, is how you let's say encode let's say classical vector into a quantum space, into a quantum state in a wise way, and but most importantly in a fast way. Okay, so that will help, I guess, us different direction. For what concerns HPC, yeah, I think in general we'll just let's say enlarge the amount of algorithm that could be feasible for us. Okay, so
I mean, does it make sense to, for instance, emulate QRAM in your emulators or not? I'm wondering if this makes any sense.
Yeah, probably yes. Also, probably this could go in the direction of trying to understand which architecture for the QRAM works better. Right. So that could be good. Yeah, but we didn't think about this.
Okay, it's not something you're focusing on right now.
No,
okay.
No, okay.
Good.
Not only us.
Okay, I had a question of my own. In your presentation, you mentioned about iterative hybrid implementations, and I'm wondering if you have had any experience in which, other than refining the parameters, because I suspect that's what you're doing by feeding back the output of the QPUs back into your circuit, did you come across any specific problem in which there was also a refinement or augmentation of the circuit itself? And I'm wondering if this is something that you observed or not, if your cases were so kind of fixed in a way or well defined in terms of the circuit that really did not make sense.
Well, yeah, we basically, so our approaches that we did were, let's say, of the first kind. So basically we updated the parameters, so without changing the circuit too much. Yeah. So yeah, it was like, so, but this other direction that you are talking about could be, yeah.
Right, it's a more dynamic, let's say, dynamic quantum circuit. I'm wondering if that can be captured in the quantum itself, and basically it does not necessarily make much sense. So it's a little bit coming from the classical view of circuits.
We didn't tell. we didn't look in this direction. One thing that we could do, I think, is, yeah, of course, could be interesting to let's say run in parallel different circuits and see, let's say, which behaves better. So,
right, okay. Exactly, right. So I'm wondering if there's also questions being posted on YouTube, possibly. So we need a couple seconds here to give Professor Rui Maranhão some time to look it up, because I had a couple more questions, but I don't want to monopolize here some of the discussions.
Yeah, no questions from YouTube. You can go ahead, Pedro.
Okay. So you support in this emulation these languages like QCT and Circ, and even this Python interface. In your experience, how hard was it to say map a problem into this language themselves? Because I'm more interested in that compilation step, that is bridging that gap. Seems to be fairly complicated because of the somewhat focused nature of the quantum circuits, so to speak. So I'm wondering what has been your experience in that mapping, yes, for quantum chemistry, it was kind of straightforward for some of the optimizations in the QUBO paradigm, let's say, was kind of also straightforward. I'm wondering if for other domains like finances, where it's not strictly that clear of an optimization, how do you see that? Essentially, I'm trying to gauge here that the difficulty of that bridging that gap.
Okay. So Riccardo, the technical part, and then I will add.
Yeah,
okay, yeah,
exactly. Yeah, exactly. So this is a more broader question.
Yeah. Okay. Let me say. Okay, for what concerns quantum annealing, we relied on basically on what the wave, what is done in the wave libraries. Okay, for, let's say, the compilation. Probably, as you know, you have to, let's say, embed your QUBO problem in the quantum architecture.
Right. Exactly.
And one thing that we have seen is that so we both tried to so different things. For example, to approximate the QUBO in order to fit directly on the machine,
right,
or split the problem in different sub-QUBOs.
Right.
And so run each sub problem on the device. So that's one thing for annealing. For what concern gate model, okay, we didn't take into account too much the compilation part. For the emulation, what we did is so for QCT and strawberry fields, we had an interface. So basically, you can write the code and the circuit in QCT or strawberry fields, and then let's say you create a file that is something like a CASM file. It is something that is pretty standard, let's say, and then we use our emulator starting from this. Let's say at the end is something like a text file, the CASM, so it tells you how the
So before Daniele falls off, just a quick interjection there. So do you see an opportunity for, say, a language that could bridge that gap over there, so that I could go from a chemistry problem in which I specify what I'm looking for in terms of optimization, or even equivalence of solutions, and then recast as a QCT circuit so that you can bridge that gap? I'm wondering if in your experience this would be highly desirable or not. Of course, desirable is one thing; whether or not it's feasible, it's another one, right?
Yes, that was exactly what I was going to say in this. For this topic here, because we think that we will have to move on, because we see the future in especially talking about hybrid HPC and quantum computing programs. In the future, I see libraries written by experts like HPC and quantum computing experts that will provide libraries that you can use with maybe with a Python frontend that you will use only to record the function that you need to the hybrid algorithms that you need in your code in order to solve your problem. And you will not concern about compiling, about writing quantum computing code in particular, because the fact right now is that quantum computing is something that is not so easy to understand if you not studied it for almost 6 months, 1 year, something that is not really something that you can afford only having a knowledge of classical computing, and it can be hard to implement algorithms that you don't know in particular, and we don't see the need of this. Okay, so we want to realize a high-level platform that can be used, especially from industrial research that have no interest to learn quantum computing or HPC, but maybe calling a simple function in Python, they will use our supercomputers connected with a series of quantum accelerators. And in this way, you can use a lot of different technologies without using the software needed to activate that.
Okay, there's actually a related question to that here on the chat, which is essentially asking if you're working on quantum programming language such as Silk or Q#. I don't know if you.
Not really, because it will be a black box for you, because we will choose the most the goodest language programming languages to program our QPU and CPUs. But yes, for the end user, we think that Python is more than sufficient.
Right. Okay. Or so that you anticipate or foresee that that's your interface, and you hide all the other technologies, let's say, inside it. So okay, good. Yes, it's clearly a widespread known interface, and so that facilitates the access, which is very important. Lower the barrier of entry. Okay, I don't know if there are any other questions. I do not have any question. Rui, perhaps, I don't know, some of the question online.
No other questions. I think we can wrap up.
Okay, good. Thank you very much. Well, let's wrap up. Thank you again for your presentation and taking the time to present and describe the efforts going on at Cineca. I'm sure that some of the attendants and some of the people who basically be watching this later on will find it useful to have these links that Riccardo also mentioned. And I have your emails. If anybody needs them, they can basically send either to me or to the Quantum QCTalks web email, and we can follow up. Okay, thank you very much. Just a quick reminder here that because of this slight change of schedule, we're going to have another QCTalks presentation right next week, next Wednesday, and incidentally, it's precisely about quantum chemistry. So it's kind of very in the sequel of this one. So hopefully we'll see many of you pretty soon. Thank you very much once again, Daniele and Riccardo, for your presentation.